So we'll leave this course with the standard model. Kind of a nice full circle in a way. I usually feel like you start grade 9 learning about the atom, and that seems like a lot at the time, right? You got to remember, okay, there's proton, neutron, and electron, and what their charges are, where they are. Pretty much in grade 9, we say, listen, like there's this little electron here in the whizzing around. And oh, sorry, if you got some atom, right? We got these electrons in these orbitals. They're basically massless, right? We don't even know because comparatively, they're 1/2000th the mass of a proton or neutron. So don't even worry about it. And then you do learn it. Okay, it does have mass, and on we go. So now we're gonna take that and just give you a whole zoo of particles. And the first thing we look at is antimatter, right? And this was from Dirac in 1930, he was trying to combine quantum theory. One of the current real challenges we still have is trying to combine quantum theory with general relativity, right? It's just, we don't know how to do it. But at that time, he was looking at special relativity, which we looked at and figured out some equations. And one of the problems was, though, it really said, well, at least mathematically, there should be all of these, other particles that are the same, but just their properties are different, right? Their charges are opposite. So, this here, then, this would be a positron, right? Just like an electron and every other way, but it would have a positive charge instead of a negative charge. We have observed these things. We definitely see them in cosmic rays, best sort of picture I could get. We see them in particle accelerators and whatnot. And so it definitely turned out to be true. And it was, one of those cool things where it was, the math said this and then, it turned out. So here's I try to just copy some of these lists just to give you a sense of what these are. So if it's an anti-particle, it tends to just have this little line over the top of it, and you'll see, like, in terms of mass, exactly the same. It's just the charge is opposite, right? Which just works out kind of cool. And we really have been talking about protons and neutrons and stuff quite enough, right? So if we actually look inside them, or what seems to be there, they're not elementary particles. It's elementary particles that make quarks are these elementary particles that make up protons and neutrons and other hadrons. So you've got, how you've got atoms make up molecules. And hadrons quarks make up, let's put that on top. All right, so just to give you kind of a connection between them. So what is a hadron? Well, you put quarks together, you get a hadron. For example, a proton and a neutron, right? Those are hadrons. Sorry. And so that's kind of neat. So the names were kind of interesting and in some ways not very original, in some ways odd. In terms of the names, we give them up and down, right? So you've got an up quark and a down quark. So a proton is 2 up quarks and a down quark, and a neutron is 2 down quarks and an up quark. I find this, I remember finding this quite baffling, because we know the charge of a proton is 1 and the charge of a neutron is 0, right? So what does that mean in terms of up quarks and down quarks? Right? What that means is the charge on these things, right? An up quark then has a charge of 2/3. and a down quark has an electric charge of -1/3. So you put these three together, you get a charge of 1. And then for a neutron, right, 2 down quarks gives you -2/3 plus 1 up quark gives you your neutral charge. Which I guess I just found really interesting because electrons are elementary particles and they have a charge of 1. So it just felt like it worked out really well then that you put these together in this way, and this seems to be stable. Protons seem to be the most stable. They may decay over like, I don't know, trillions of years or something like that, but they're generally pretty stable. Neutrons are not. They're stable in nucleus with protons on their own. I think they decay in about 15 minutes, and they have a little bit. If you look at their actual energy or mass, up here you can see that just a little bit more if you compare proton and neutron, right? So it really is that particle, when they can get into this lower energy state, they do this pretty quickly. And in terms of how most things decay, that is like eons, right? Most of these can decay in fractions of milliseconds or less, right? It's quite quick. So quarks interact via the strong force. The way I would look at that is, what holds them together? If you think about it, you've got, the electric force, you kind of have a sense of it. If I put, if you compare that to electric force or something, right? It's like, well, right, I put a positive charge here and a negative charge here, and there's some force between them, right? Just because they have this property. Similarly, it's kind of the same. If you have two quarks, they experience this, and a little bit like gravity, it tends to be attractive, right? And so really that tells you, well, yeah, why do these things even stay together? If the electric force, even if you look at a proton and a neutron, the electric force, or two protons rather, right? The electric force should be saying, get apart, right? Go away. But so the strong force, so named because it's much stronger, this is like 1,000 times stronger than the electric force, is basically a attractive force that keeps them together. The problem is it's very, very, very short range. So once you get a few protons away, they kind of start to balance out. And this is why larger nucleuses are not as stable, and why it's not as you don't actually get energy if you look at fusion or whatnot. You actually, iron's about as good as it gets, right? And then after that, the electric force seems to be stronger between the ones that are farther away. So here you've got let's just say up and up and I don't know, but they're attractive. Again, just some naming. So a baryon is just example of proton. It's just a hadron that's made up of an odd number of quarks, whereas a meson is made up of an even number of quarks. They tend to, again, they're very unstable. Mesons even don't seem to be very stable, which is a little bit interesting, whereas baryons, like protons and neutrons, are relatively quite stable. But if you try to put like 5 of them together, whatever, again, just not stable. Doesn't seem to work. These seem to be, well, this is pretty much all the matter, right? Protons and neutrons. We don't see much of this other stuff except for very, very short periods of times in like particle accelerators, or like I said, maybe in some cosmic rays or something with really high energies. You might see some things for little bits of time, but they're things. As promised, the names are quite weird. So we know about the up quark and down quark now. Those are the ones that make up protons and neutrons. But then we have the next level. We have very similar to them, just much, much more massive. We have the charmed and the strange quark. And then the third level above that, we have the top and the bottom quark. So they're very similar in terms of like properties and whatnot. You can see if you look at, if you look at a charmed, right, it's very similar to an up quark, right, in terms of its electric charge. But if you compare their masses, right, um, you're given a bit of a range because they do, right. Technically, they all range, right, and you can see it's a bit of a range of this idea that we have this number for the mass of a proton. It's, well, not really the case. Like, proton from proton to proton, it's there's actually going to be a bit of a range, and from time to time, there's going to be a bit of a range. As I said, they're quite weird. But if you compare these just in general, you're looking at masses of like about 1 to 3, and giga is 1,000 mega, right? So this is like 1,000 times more massive in terms of energy. So yeah, they're not going to last for too long. And then this, you're looking at even relative to this, right? You're looking at almost 200 times that. So these things just, very, very massive, incredibly unstable. But quite interesting. Here's just a few baryons. Again, the only ones that really are stable or that stick around is the proton and neutron. Everything else, as you can see, the times here are not much. But they exist for little tiny bits of time. That brings us to leptons. So we got quarks, and then we got leptons. So leptons, electron, that's probably the big one that you know. These are elementary particles. So the main difference here is they do not interact via the strong force. Right? So, but they do, of course, interact via the electromagnetic force. So that's really their interaction. So if you look at an electron with a proton, that's what we see. So basically, for these, you're looking at like electron, muon, and tau, and then each of those has their own neutrino, which are neutrinos are very, very, very light. You thought electrons were light; these things are like 10,000 or 100,000 times less massive than these. Are extremely light. They don't really interact with much. There's probably like, I don't know how many billions of trillions of these things flying through you right now. You don't notice it. They don't do much, but they're there. You can see the symbols. You can look at that again. Remember, they do have antiparticles for all of these things. There's going to be an antiparticle version. And that's the end of. So if you look at those together, so fermion is a general term for a matter particle. Named after Enrico Fermi. And those are some of the ones we were just looking at, right? Like baryons and leptons. And these are like, so that's a class of particle that makes up all of this stuff, if you want to think of it that way. And then we get to bosons. I can't say it right. Bosons. I don't know why I can't talk right now. But these are force carrying particles. And I probably have it listed underneath there, but yeah. So we've done a lot in this course with forces, but we've never really asked, well, where does this come from? How do these forces originate, right? It's just sort of, you have this sense that, well, if I push something, it moves. And if you really break that down, it's, well, why, right? Well, if I'm pushing some object here, and let's say this is just part of your hand right here. I don't know. I can't draw. Probably do a little better than that. There's a hand. You're going to push this object, right? Well, if you zoom in on this really, really well, what's going on here? And you'd say, oh, well, that's probably the electric force, right? Like if you looked at it close enough on a molecular level, you're saying, oh, yeah, there's these electrons and electrons there, and they're repulsive, right? So you can actually touch it, and that sort of works. But then, well, why is that, right? What is it that makes that happen? We know atoms, right, are mostly empty space. Um, we do have definitions of things touching, right, when they're actually a certain distance apart where the energy is lowest. We can say, yeah, no, they're touching. So that's doesn't really solve that or anything. So what actually happens? Well, as best we can figure, there's particles that are exchanged, right? So what leads to this electric force? That is that when you zoom in here, you've got these two atoms, if you will, that are really close to each other, and these electrons here and electrons here, and they're saying no, stay away. What's actually happening here? Why would it do that, right? We already just saw that there's this wave particle duality. Why doesn't the thing just go through the other thing? Or what's happening? And it's like, well, what they exchange a photon. So this photon, these particles we've been dealing with as light particles, are the particles that seem to carry, if you will, or communicate this electromagnetic force. Now, how exactly this works, I is kind of weird. I've tried to see or look at some explanations. I never found one that's really good. This seems okay if you consider repulsive force, right? If you've got two charges, you're like, well, okay, there's photons go back and forth. Probably an important reason why light is this, speed limit of the universe. And, you can imagine it's sort of like a ball, being passed back and forth between two people. And it's like, oh, yeah, well, as one catches the ball, maybe they move away and okay. But then what about the attractive force, right? It's like some sort of boomerang that they throw. Well, then the photon sort of acts like a boomerang and comes around this way, and they move closer together. So yeah, I don't really know. Like it's just to me that's one of those really baffling and really interesting things that they just send photons back and forth, and somehow if it's one of these things that we say has a positive charge and the other particle, if you will, is something that we say has a negative, then they just know, right? Okay, somehow the photon that is sent between them leads to them moving closer in space, right? And again, there's no other force there, right? This is the thing that leads to the other thing that we say is a force. So somehow, so it's not like there's resistance or anything here, but somehow when one photon is received, it somehow knows, and or there's something about that makes it move closer, and in other instances makes it move away. Bizarre. So the other force, as we mentioned, the strong force, that's a different type of particle. That's a gluon. And you've heard of the weak force, the weak nuclear force. That is the W and Z bosons that communicate that force. So, and that's why I said quarks, remember, don't interact via the strong force, so they don't. The gluons, they don't really do that. Whereas they're all about the electric force. And that leads us to, a little summary of all these things here, just in terms of their symbols and the lovely Higgs boson in the center of the whole thing, which seems to be that all of these things interact with this, and that somehow leads to mass. I guess in some sense, it's like it is interacting with this sort of gives you some ability to slow down or whatnot, and then the more you interact with this, right, the more it leads to this type of energy, or that would ultimately be considered, or something that would give it the property of mass. Field theory. I'll leave it with this because to me this is kind of the coolest thing about all of the physics we've done and all of the you may do. And this is just the fact that all the evidence we have for particles is indirect, right? I've somewhat mentioned this before, but what we see is how the quote unquote particles fields interact. If you think about it, well, all the stuff we've talked about with electrons, we just talked about how they interact, right? Well, they have this force, electric force, right? And they have this mass because of whatever energy that is sort of stored there or exists for that time. But if you look, or even at particle accelerators, and when you see what comes out, or really you're just seeing these effects, you're just seeing how the field that it has interacts with these other things. If we don't see those interactions, how can we say there's a particle there, right? So there could be all kinds of other things that just don't interact in any way, and we have no way to detect them, right? So the particles we see are localized vibrations in quantum fields, right? Everything really is just fields, right? There's no, particles. It's just, fluctuating and changing in superpositions of fields that influence each other. And on a large scale, it's convenient for us to say, oh yeah, there's an electron there, and there's a proton here, and this is how they interact and whatnot. But at the end of the day, it's all just interacting fields.